So I think we're all a lot of us are interested in simulating nature, and I'd like to tell you a bit about how we're thinking about doing the quantum information processing aspects of this. I'm Eleanor, and I'm a postdoc at MIT. So there's, in all these different areas of science, bosons, which, for example, phonons or photons, interact with fermions, for example, electrons or quarks. And this leads to a range of strongly correlated phenomena. There's been a lot of progress done towards solving these sorts of problems with classical methods and also analog and digital methods. However, it's a strongly correlated fermion-boson problem, and the different parts of the problem cause issues for different approaches. So field theory, for example, struggles to get controlled approximations at strong interactions, or you need special symmetries. Quantum Monte Carlo struggles with the fermionic aspect of the problem, or the dynamics, anything where there's a sign problem. And it's the bosonic side of the problem which causes issues for other classical methods. I just wonder if this needs additional, maybe I need to point it somewhere. Does anyone know where I need to point it? Like here or here, seems good. Okay, and so you would have thought this is perfect for analog quantum simulation, which it is, but for the purpose of this talk, I'm going to argue that you can't, with analog methods, get a universal set of operations, so we can't look at all Hamiltonians or all observables. And so we would have thought that digital qubit methods can, in principle, solve all of these problems. But for the bosons, and in the context of large spins, if you're more familiar with large spins, bosons are essentially very similar to large spins. You have this this huge Hilbert space, theoretically infinite, except that a large spin is basically more symmetric. You have theoretically infinite negative and positive Hilbert space, whereas here it's positive. And importantly, the action of the creation and the annihilation operators, so what takes you up and what takes you down, your Hilbert space, is not the same for a boson, whereas for a large spin, you're more symmetric. So the problem is with bosons. The problem is with bosons, mapping them to qubits, the large Hilbert space is expensive. And also, this action of the creation and the annihilation operators is also hard, because on qubit platforms, it's not very good at arithmetic. Square roots are kind of tricky. And for the fermions, it's the anti-commutation relations that are hard on qubits. So I'm going to also put these on the graph of large boson occupation and exploration of this Hilbert space during, for example, the dynamics. And I'm going to say that they can't actually also access very, very large boson occupations. And yet, there's a range of really important open problems in this regime, which is difficult to access with all existing methods. And so why not just extend our quantum computer now to contain the fermions and the bosons and use them in a digital way? Essentially, instead of this, why not just do this? And avoid the overhead altogether, and also be able to solve, in principle, all strongly correlated fermion-boson problems. There is a range of platforms which have demonstrated this joint control over various degrees of freedom. But the problem that we really have to answer is, can this hybrid simulation be done? And if so, how? And what's the advantage over the existing methods? So let me take you through one possible platform. We won't spend a lot of time on this because Ben Brock introduced this yesterday in the context of the GKP error correction. But essentially, this is, in the following part of the talk, I'll just consider that we're using this platform, and the kind of connectivity that we have is we have large bosonic modes connected via beam splitters, and each mode is connected to a qubit. So let me explain. We have this kind of aluminium box, which has a hole where we put a microwave and a transmon qubit, and they interact. So cavity is the boson, hosts a bosonic mode, which can have many bosons. We can have a Bose-Einstein condensate. And it can couple to a qubit. And the cavities, or the cavity modes, the bosonic modes, interact via a beam splitter. So if we detune the qubit from the mode, we can go to this dispersive coupling interaction regime. And the dispersive coupling interaction regime, you can now absorb this term into the qubit term or into the oscillator term. Or, down here you can see that the qubit frequency is now dependent on the number of bosons in the mode. A dagger A, that's just n, that's just counting how many bosons do we have. So now you can see that the qubit frequency is in fact shifted by A dagger A. And and this is a relatively well-established platform. We can look at count the number of photons, and people have done initial demonstrations of looking at spectroscopy on molecules, edge states, and topological models, error correction in grid states that Ben introduced yesterday. So this is kind of very promising and relatively well-established, and we know how to use these sorts of experiments quite well. So, okay, to begin with, let's just map a simple model. For example, the 1 plus 1D Z2 lattice gauge theory in the Higgs sector. So this has got Higgs, or kind of, we say in the Higgs sector because it has bosonic matter on the sides. And people have looked at this in the context also of error correction with hardcore bosons. But here we're really considering the case where every single site can have a theoretically infinite occupation of bosons. And in the intermediary between two sites, we have the gauge fields, which are going to be just mapped to qubits. They're just Z2 gauge fields. So you can see the first term, that's just a field term, try to align all the spins in the same direction. The second term, hopping, that's basically every single time a boson hops from one site to the next, it flips a spin. And the on-site term, U, energy penalty if you have multiple occupancy. And we can even consider an extra term, the bosonic density-density interactions. There's Gauss law, might not be super relevant for this talk, and very few people have kind of looked into this bosonic Z2 model. There was a study on cold atoms where they went to two sites. So it's a challenging kind of area because you have both a qubit and a bosonic degree of freedom. So what do we want? We want to implement, for example, the Trotterized Hamiltonian. So we want to implement these sorts of gates. And do we have these gates as native gates? No. So what we do have is access to this instruction set architecture. So let's go through some of these terms. Firstly, this electric field term, super simple. It's just a Z rotation on a qubit. Secondly, the gauge invariant bosonic hopping. So we can actually, this trick is the workhorse for a lot of the rest of the work. We in the rest consider that you can always control a bosonic operation on a qubit. So we have a beam splitter. Maybe in fact, let me put this full circuit. You've got the beam splitter part of it, that's good. Now we need to control the beam splitter on a qubit, and what you can do is you can essentially sandwich it between these controlled parity operations. And if you calculate this is based on the BCH formula, Baker-Campbell-Hausdorff formula, then you'll see that you get an exact equality at the bottom there. And I've just added the Hadamard gates because what you get is a Z-controlled beam splitter, and here we need it to be controlled on X. So now in the rest of the talk, I'll just assume we can control any bosonic operation like a beam splitter or a displacement or anything on a qubit. What about the on-site term? So here we saw that the qubit frequencies depend on the bosonic occupation. So we can actually just make a rotation on the qubit, which is dependent on the bosonic occupation. So why not, and this is a bit of an outline of how this gate works, but why not use this gate, which is called the selective number-dependent arbitrary phase gate, where you can essentially, if you choose theta n, so you choose the phase of your gate, for every single different Fock mode, you can rotate the qubit differently. So when your Fock mode is 4, you just choose that your phase of your gate is 4 squared, and then you're basically done. And this really comes from this interaction between the qubit and the oscillator, and the qubit frequencies depending on that. So this is just all completely done in one single gate. And then what about this kind of nearest neighbor or density gate? How do we get the NN gate on two different modes? So it's a little bit more lengthy, so I'll take you through one or two slides. So firstly, we want to make a parity conditioned gate. And so this is also the snap gate. I know that's not unitary, but just imagine that you also apply identity on the even Fock states. So this gate is saying because you have a projector on your mode, you just flip your qubit if your mode has an odd Fock state. So now your qubit is only in 1 if your mode was in an odd Fock state. We can now apply this any bosonic operator, as you said, controlled on a qubit. So now this Z operation gives you a phase only if you're in 1, only if your mode was in 1, which is equivalent to saying, well, in fact, let's just give a phase to the odd Fock states. And now you apply the snap gate again SQR gate again to bring it back. And so now what we've compiled is exactly a operation which has a phase given by the parity, or a phase which is dependent on the parity of the mode. Here we just using, you undo it if you didn't want it. This is just saying if you only give the phase if the parity is in a set state, as opposed to which is dependent on the parity. And then you can apply this many times to actually, in binary, encode n as opposed to the parity. So the first gate gives you a phase if you're in one of the red Fock states. The second gate gives you a phase if you're in one of the red Fock states on the second line, and the third gate and so on. So you can take, Fock state 3. Basically, in binary, you can basically compile n times any other bosonic operator. And actually, the readout takes the similar is based on a similar principle. Okay, so we can do all of these different gates which we need. And now we used bosonic Qiskit, which was a wrapper that we made for Qiskit, which is IBM's open source platform for coding with qubits. And now this wrapper allows you to code with digital bosons and digital qubits. And we made some simulations of what the circuits which we'd created, what kind of dynamics do you get? So if we go to this, just the field with the competing hopping term, you can see that if you're in a very, very strong hopping regime, then one boson in the center of the chain, so along X we have all the different sites of the chain, we have one boson, and then we're time evolving along Y. So this boson has a light cone spread because you essentially just have strong hopping. But what happens if you now have 2 bosons? So I remove site 0, I take out one boson, I just put 2 instead. So for 2 bosons, if I'm now in the case of a strong field, or let's already just take, let me take one step back. If I now have this single boson and I have a strong field, I can no longer hop because the gauge invariant hopping causes the field to flip. But if the field is really, really strong, it avoids any hopping from taking place. But what happens now if I have 2 bosons in the central site? This is the case of strong field. What happens is, and maybe some of you are already thinking this, is you can not have one single boson hopping, but you can have 2 bosons hopping. So now perturbatively, you again get this strong light cone spread. And we can more or less see this with a theoretical simulation, which is along very, very realistic experimental parameter regimes. We also looked at ground state simulation. So this is kind of looking at a VQE, and we're doing VQE for all of the parameters in the Hamiltonian being equal to 1. And what we see is the black line is essentially an experimental. It's just really to show you that we've kind of we're starting to benchmark these methods. And so what we see is we are able to get a ground state energy, including some of the main sources of experimental noise, which is below that dotted line, the red, which is the first excited state, and it's near the ground state. The energy of the ground state is at the 0 of the graph. And we're even able to do a little bit of Gauss law error mitigation, which we only included here on the last step. And we see that, basically, even including noise, we're able to start to get some kind of ground states. And this is maybe one too many for now, but basically, we can measure some long-distance string order correlators as well, because it's a digital method, of course, and we can decompose this creation and annihilation operator and make a Hadamard test. Okay. So I just wanted to go on to, so really quickly have a quick look at what the time is. Oh yeah, perfect, thanks. Okay, thanks. Okay, so what about the 2+1D U1 quantum link model with fermionic matter? So this obviously approximates quantum electrodynamics and the limit of large infinite cutoff. infinite cutoff. And if we want to map this to qubits, and maybe this is kind of the wrong audience to be talking to you about the fully qubit version, but if we want to map this to qubits, then we need a number of qubits which is logarithmic in this cutoff. Here, what we want to do, of course, in quantum simulation is look at all of the dynamics and the ground states. So there's many different terms in the Hamiltonian, but the hardest one is this plaquette magnetic field term, as we were hearing yesterday. And the problem is that not only is this qubit register very deep, but you actually also need very long depth circuits, which actually scale linearly or logarithmically in the cutoff. So why not use bosonic modes? And how would we do this? How would we map them to experiment? We use a Schwinger boson encoding, and there would be different ways of doing this. I mean, GKP, grid states, this could be GKP QuDits, and we could go from a boson to a QuDit in this way, for example. But let's take, so often in high energy physics we're thinking about Schwinger bosons, so it was an obvious place for us to start. So we have this plaquette term, and we want to implement the large spin, and we use two modes, and so you can see there the S plus operator, which brings you up or brings you down in this large spin. And so we need to map this to the hardware, so you can see that we have every gauge field in orange is mapped to two modes, two cavities. And now if I rewrite this magnetic field term, in terms of the Schwinger bosons, I get this product of 8 modes, and this is tricky. How do I get 8-wave mixing? Especially when all I start from is 2-wave mixing. So what we're actually able to show is you can use the Baker-Campbell-Hausdorff formula. If I apply a beam splitter conditioned on a qubit, using the previous trick that I was telling you about, and then whatever Hadamard's are required to rotate that qubit around the Bloch sphere. So if I now apply a beam splitter on A and B modes commute with C and D modes. So what's really nice is when I calculate this Baker-Campbell-Hausdorff formula, I can pull O1 and O2 out of that commutator because they commute. And what's left is just the commutator on the qubit. And so I now add my beam splitters, and I see that I've managed to get 4-wave mixing. I have some additional terms here and here, which are not going to appear in here. So I can cancel them using Trotter. So I apply the same thing again with the inverse phases, and I can cancel them out. And now I've gone from 2-wave mixing to 4-wave mixing, and you can imagine how you can then get 8-wave mixing. So this is really neat, because this is what's essentially constant circuit depth versus these previous circuit depths, which were increasing with cutoff. And so, in fact, let me quantify this just a bit further. This was a previous result for the U1 lattice gauge theory, and this is the full, all of the dynamic terms. And so you can see here, as a function of Hilbert space cutoff, you need an increasing number of entangling gates, whereas the qubit boson method that we were just discussing is of order 1 depth. And in fact, if we now add this Z2 lattice gauge theory of bosonic matter, it has an even, actually there were no qubit algorithms for calculating this, and we had to figure it out, and it's super expensive because of the action of the square root and the action of the creation and the annihilation operators, but we see we get an even worse prefactor, and this is really because of the bosonic matter, whereas for the U1 lattice gauge theory, we just needed a large spin, and so there's no square roots required for us to make these calculations. And yet our circuit is supernative in these platforms, and it's of order 1 depth. So this is good. So we now kind of, we have extended our quantum computer to contain the bosons and the qubits. And the question is now, what about the fermions? Right, and you can see that I've edited my slides slightly late, and Alex's face is still there, but this is good because this is someone who is really helping me with this work. Thank you. And so we need to think about how we can actually encode these anti-commutation relations. For now, on a all-qubit quantum computer, let me just see one last time if I can move this mouse. Yeah. On an all-qubit quantum computer, we obviously need to do, fermion-to-qubit mappings, and these can scale with the square root of the system size. But what about just using native fermions to model fermions? And actually, this was done recently by various groups who made a big collaboration. And they've made a very nice paper where they've actually demonstrated that you can do universal fermionic quantum information processing in neutral atoms. But one of the problems that they faced was that the phase errors were causing, very, very low depth circuits. And so kind of makes it very limiting to be able to use this method at all. So then we thought, well, we can actually still work on this. And what we can do is we can correct. We can use error correction to go from fermions to fermions. And so we preserve some of the properties of the complex fermions through to the logical level by using Majorana error correction in the end. So we're extending the Steam code. And so, yes, we can kind of error correct fermions to fermions. And also, this is the comparison is, you get this, order 1 depth circuit compared to these circuits which scale with the square root of the system size. Good. And actually, Alex was looking at, because that was, in the Rydberg atom platform, you can have these native fermions. He was then looking into, can we actually just also include the bosons into this platform? And then we have a fully fermion boson platform, all within the same architecture. And so what he showed is how you can actually, engineer a beam splitter. So there's 2 citations there. One is some of the work which he used, and you can see this is his contribution here. So that's why his face on there. And so we have the fermionic aspect of things, and we have the bosonic aspect of things, and they might all be able to be combined within this one single unifying platform. So to finish, I'd like to thank my collaborators, and maybe, especially also Steve Gervin and Nathan Wiebe, who have really been pushing this qubit boson direction with me, and Kevin Smith, who's another postdoc also, who's been working very much on this with us, and Michael Gulans, who's been really helping with the error correction, and basically the whole team. It's been good fun. So, yes, to conclude, we've shown some strategies for being able to actually use qubit boson quantum information processing, and maybe also include the fermions, which may be promising for this kinds of lattice gauge theories and other models. Thank you.